Alright, so I have my tuning slides all pushed in as far as they will go. They're all the way in. And I have my right hand completely out of the bell of this horn. Now I'm going to see where the intonation is going to be. I'm going to play a concert C. Alright, so the C is actually in the space of a C sharp now. So the horn isn't in F, it's in F sharp. Now the concert C turned into the C sharp in 432 hertz tuning. So you have 432 on one side of the pitch and 432 on the other side of the pitch. Now, it doesn't matter if you're going to go ooh or ooh. Both of those notes are still going to be in the same tuning system. So if you're going to tune to ooh, you can actually tune your C to that B. It doesn't sound as good. It's much too low, but you can still tune it quite low and still make it sound like a tune. Alright, so 432 hertz as your C, or as your A and playing a C, you'll get C. Now, that's just tuning with the tuning slide halfway out and using a reasonable right hand where you just covered the bell halfway. So I'm just using my ear and the natural harmonics of the instrument to play where the instrument is tuned. Now, musicians are tuning to 432 subconsciously and trying to match 440 hertz standard pitch. So they get ooh. So they go just as high as they can without changing the notes, just to be able to find their standard pitch. Now, your tone quality can suffer if you play like that. So what you want to do is have a more radiant sound. You want the overtones to be more magnified, to become more audible. Now that's just standard pitch. We're going to go all the way up to 448 hertz. So your C in that tuning will go ooh. So it sounds like a flat C sharp because technically it is. Because technically and literally 448 hertz is an octave of 7 hertz. Now 7 hertz comes from the 7th harmonic of 1 hertz. Now the 7th harmonic is a B flat. That's just common knowledge. And 1 hertz is an octave of 2 hertz, which is an octave of 4, an octave of 8, an octave of 16, an octave of 32, and then 64, 128, 256. Now 256 would give you your scientific pitch. That's why it's called scientific pitch, because it comes from the root of measurement. Basic numbers, 1 hertz, 1 beat per second, turns into 256 hertz middle C. Now, 41 octaves above not standard, but scientific pitch is the color green. That's just how the numbers match up. You have visible light that's measured in terahertz frequency or in the trillion hertz per second range, but it's still hertz. It's still simple vibrations. So you have time, sound, and light, the three things that make up the third dimension that are all connected on this energetic level. So you have 448 hertz tuning to A sharp. Now, if you have absolute pitch, you might have to think about those notes for a second to be able to recognize, oh, it's closer to C than it is to C sharp. And then you'll be able to recognize where it is in the frequency space. Now, if we're going to go up from 448 hertz up another 8 hertz to 456 hertz, what happens to the C? Ooh, it turns into a C sharp. Now, 456 hertz is when the octave completes. Now, in tune, if you raise the frequency, it becomes sharp. If you continue to raise it, it then becomes flat. And then if you continue to raise it, then it becomes in tune again. Alright? Now, at what point is sharp going to turn flat? And at what point is flat going to turn in tune? You see what I'm saying? Now, if you're going to tune your tuner to 456.1 hertz, you get ooh, and it still sounds like the same frequency. That 0.1 hertz difference isn't going to change how you hear and recognize that specific wavelength. Okay? Now, it's not like we have computers in our ears telling us which notes to play. That's not how this thing works. So in 456.1 hertz, you get your B at scientific pitch. So your B becomes ooh, that's C. So that's when one note becomes the next, when it completely shifts, when it completely turns into the next, when it completely shifts the octave. So you have as your B without the right hand with all your tune slots pushed in, or you can turn it into your C by going down a half step. You just pull your main tuning slot out halfway and cover the bell halfway. So you're keeping everything in the middle. And it's going to be around this scientific pitch. So it's the same frequency space, but the timbre is what changes. It goes from bright to dark. Now, we're not confusing bright with thin. Alright, so 456 hertz, we're going to go down 4 hertz to 452 hertz. 452 hertz will give you your quarter tone in standard pitch. So that's your perceptual quarter tone in standard pitch. Now, technically, it's in the C sharp range. You can hear and I would instantly think C sharp before I would think C, just because that's where it is in 432. Now, I didn't always know that 432 was the root of my absolute pitch. I didn't always know that 448 hertz is an objective B flat. I was like, I just knew that there was something wrong with how things were, and I looked into it and figured it out. Now, standard pitch 440 isn't necessarily wrong, it's just sharp. If you make sharp in tune, then it's better to be sharp than out of tune. But it's even better to be in tune than to play sharp. Now, in tune is wherever you're going to put your frequency. Now, we're going to go down 4 hertz from 452 to 448. We're going to go down another 4 hertz to 444 hertz. Now, these 4 hertz differences aren't going to be completely audible to the untrained ear. Okay, now we're going to go down to 442 hertz. Orchestras like the New York Philharmonic, they specifically tune to 442, but I don't see why, because they don't really stay there, so they might as well just listen to standard pitch. Now we're going to go to standard pitch. Now you're going to hear what in tune sounds like. Alright, now we're going to go down another 4 hertz to 436 hertz from 440. Now 436 from 432 sounds 15 cents sharp, but the tuner from 440 will tell you that it's 15 cents flat. So it's in this mystical space range where the lift is there, your standardization of pitch would allow it to still sound sharp, so it still sounds in tune. And then we can go down another 4 hertz to 432, so that we get our 256 hertz C. And we can even go down to 424. Let's go ahead and bring it way down. So, ooh. So your 424 hertz is going to be an A flat when you tune your A to 448 hertz. So 424 goes to 432, which goes to 440, which goes to 448. Now, like I said, 448 and 424 are in the same recognizing space. It's just one's an A flat and one's an A, or one's an A and one's an A sharp. You see what I'm saying? So you have 36 tone equal temperament, where each tone is divided into 3 parts: sharp, flat, and in tune. Now, if you're going to put your intonation in 432, that's just where the pure colors are. It just so happens that when you tune your A to 432, you get your C at C. Now that's an octave of the pure green color, and that's how we're able to recognize the difference between different notes. We're able to hear the chroma. Now, chroma is the, what language is it? It's the Greek word for color, okay? Now, the chromatic scale becomes the colored scale. So it shouldn't be too much of a surprise that each note has its own color. So that's just 432 hertz. They used to say that you couldn't even play that low on these modern horns, but the tubing of these instruments haven't gotten any shorter. It's just your awareness of how it works is becoming improved. Now you have 432 at the top. You can play C sharp and push in all your tuning slides and take your right hand out of the bell, and your C will be a C sharp in 432 hertz tuning. So you're seeing how the octave has completed. And then after you've studied all these different hertz frequency tunings, you can just put it in standard pitch and play a tune. So pick your key. Do you want it in D flat or do you want it in C? Or do you want it in B? Now there's 12 different divisions. There's 12 hours on the clock, 12 notes in music, and 12 colors in art. So we use a 12-tone system, and it's all connected on the energetic level. So to master standard pitch, you have to observe 432. You just have to. That's where our notes are rooted within our awareness. You can look out and see all these different shades of green, but you can tell a lime from a turquoise. You can tell a pure green from a tertiary green. Now the pure green has a specific hertz range. It has a specific wavelength. So that's just 432 hertz tones. It's an octave of pure color. You got red, green, and blue, yellow, cyan, and magenta. And then your 6 tertiaries to get your 12 tones. Now yellow starts where orange ends. So yellow starts at 448 hertz, the 7th harmonic of scientific pitch. Okay, so now I feel like I'm repeating myself, so you really have the information that you need to know.